say we're gonna use clip angles and we're gonna have, standard center to centers, we're gonna have standard measurements down to the holes, everything's gonna be standard. But we have to understand when we come to connections like this, it has to go beyond the standards. We have to think of things like this solid object cannot just come all the way across here. We're gonna have to modify one of these objects. Engineers, whoever, have already gone through and said, if you modify this object right here, if you cut that top back on that object right there, cut the bottom back if necessary, it is not gonna weaken the strength of that connection or of that member up in the rack. So we say, all right, so when we have this condition, we know because these beams are normally top to top. There are occasions where you're gonna see one that is actually down lower. Usually it's in a bracing type scenario, but I've had them where the whole member was down inside the member it was attaching to. That meant there was no grading or any floor plate or anything going on top of it. It was just there for a frame. Maybe it's there for a pipe rack. Didn't matter. As a structural detailer, all I had to do was just visualize that instead of those coming in top to top like that, it's coming in down here. So we don't go into it saying, well, that's a beam to beam connection, I'm gonna have to block the top, I'm gonna have to block the bottom. We're gonna look at it. If it says nothing to the contrary of those beams being top to top, that is the norm in industry. Even if there isn't gonna be grading on top of it, the norm is to have them all at the same elevation, the same height above the ground, but not near all the time. The majority of the time, yes. So when you do these, we have to say, okay, what are we attaching to? So we're attaching to this beam. It is this member that we say we need to cut back to here to dodge that flange. It is this member here that we say we have to get down below that curve right there. We have to block it down that much based on that member. So as we're doing this, and you've got a formula that says take the half web of the beam. Well, now they're both beams. There is no of the beam versus the column. Now we're talking about both beams being beams. So this is the beam that you're attaching to. This is the one that we're detailing. This is the one that we're trying to say how long it needs to be, what the clip angles on the ends need to be, how far down, how far end to end. This is the one that we're detailing. But those cuts right there that we have to make are based on the measurements of this member. So when you're doing that little thing up there where you drag the dimension line up and you bring that dimension out there that says block top, or block top and bottom, and you've got those two dimensions, a K dimension that is the K dimension of the member you're attaching to, not the beam you're detailing. You've got a half flange measurement for this dimension. It is half flange of the member you're attaching to, not the beam that you are detailing. So understanding that shape and understanding what's happening. It's not just the lines that I've been drawing up here. Just little single lines like this representing that I-beam. And saying, yeah, we gotta block this one out of here to get them to fit. These lines, these objects that we're talking about, these I-beams have mass. The sooner you understand that shape and what these little lines over here in this drawing right here mean, that, okay, that's what they show us. Not a problem. I know what I'm looking at though. I know I'm looking at the top of two beams. This beam over here is a W12 by 30. This beam over here is a W14 by 34. So as drafters, up to this point, you're pretty much drawing, with the exception of the instrumentation and electrical diagram drawings, you're drawing the object as it is. You're looking and working off of something that looks like what you're drawing. Whereas in this one, it's represented just by a single line, but we know our finished product is going to look like this. So here's your rule for when to block. You will be blocking the top flange. I'm not going to give you any that you do not have to block the top flange. If you have a beam to beam connection, if you have two like this, where you've got one line representing the center line of a beam, and you've got another line coming into it. Maybe you've got a column over here, maybe another beam, it doesn't matter. We're just looking and focusing on this one right here. So on this end, it's going into a W14, a W12 going into a W14. We know that that I shape that first value, the nominal depth of each one of those, is a pretty close indication of the actual depth. We know that that 12 by 30 that we're drawing is going to be about 12 inches, top to bottom, plus or minus. We know that that W14 that we're attaching to is going to be about 14 inches, plus or minus. So we're not just going to go by that. We're going to look them up. But it's real easy, the two numbers you have to look up. Your rule is, if both of these nominal depth, if the nominal depth of both of the members, the member you're drawing and the member you're attaching to, both beams, if the nominal depth is the same, you're going to put block T and B, flange. And then you're going to tell me those numbers. The K dimension and the half flange width. If your numbers are the same for the nominal depth, W12 and W12, W10, W10, W14, W14. If your numbers are the same, you will only be damn, my bad. Scratch all of that I just said. If they're different, so backspace on everything I just said. If they're different, W12 and W14, if the nominal depth is different, you will only be blocking the top flange. If they are the same, you will be blocking the top and bottom flange. This and what you see on the screen up there is similar to both of them being the same nominal depth. Are they the same exact depth? Unless the weight and everything's exactly the same, there's no guarantee of that. They may be. There are a lot that do share common depths, common measurements. When you get out in the industry and you're doing structural steel, once again, it's going to be sometimes based on the company. It may not be as easy as the K dimension and the half flange width. Because like I showed y'all the other day, it's similar to what you see on the screen. We do have some gaps in there. Could it be tighter? Yes. Is there any reason for it to be? None that I've ever seen. I've even asked when somebody said, well, this is how we do our blocks here. Any certain reason? No, that's just how we do them. It's just a lot more work. I mean, you know, you are paying by the hour. It's a lot more work, you know, just for the drafter. To them out there, it's just two dimensions. How far down and how far that way. That's all they need to know out there. For the drafter now, we've got to look up measurements. Sometimes they say, we want 1/8 of an inch gap. What for? So we can come back and weld it. Okay, that I understand. You want it tight so you can go back and put a bead of weld around there. I understand something like that. Welding it after it's in place. Strengthening it all up. I can understand doing that when it's an option. But other than that, there's no reason other than most places just say, show me what I need to cut it to make it dodge that other member, which is what we're trying to do. So we're not going to extra cut it. We're not going to make it too short where they have to get out there and try to bang it down or something to get it into place. So a good rough number is the K dimension and the half flange width of the member you're attaching to. That's going to be our our block dimensions. That number by that number. So any questions about blocking? So the other day, I think I either printed it or put it in Blackboard for y'all, showing you that block, showing you the numbers. The main thing to remember on that is the K dimension and the half flange dimension that you're using comes off of the member you're attaching to. That's the biggest mistake on that one. Other than that, we're back to some of the other rules that we had from before. We had rules that said when attaching to the web, technically before it was when attaching to the web of the column, but it's still when attaching to the web, your center to center is 4 inches. Your minus dimension is gonna be in the 1/8 to 3/8 range. That still applies on these beam to beam connections. We're still attaching to the web. It's just the web of the beam. But the minus dimension and the center to center are gonna be just like they were. Where's your Michael see? Right there. But the minus dimension, can you set that down there for me? The minus dimension and the center to center, the little tips in the back of our head, still applies. When we had the beam to column connection, we said, all right, if it's going to the flange, it's gonna be about half the nominal depth of that column. If it was a W12, it's gonna be about -6. If it's a W14, about -7. So we had that kind of little rule that we said, all right, I can back check myself, I can glance at it and possibly tell if maybe I made a mistake right off the bat. We said that when we were going to the flange of the column, that the center to center was gonna come off the usual gauge. I told you it was gonna be 3.5 and 5.5 center to center the whole way through. And sure enough, I went and gave you an assignment that had an exception. So a lot of these do have exceptions. I try not to throw too much of that at y'all. We talked about how the W8 beam, the first hole down is down 2.5 instead of 3 inches. But I didn't want to throw that at you. I've mentioned it a couple times. We actually seen it on one of the handouts or one of the, maybe something that I put in Blackboard for you. One of the details similar to what I just gave you. That showed you a W8. And I have a note that points to it, says when using W8 or something like that beam, first hole was down 2.5.
Mr. P, you said the width was going to be half the flange?
Of the member you're attaching to, yes.
Of the member you're attaching to?
Yes. So this is, what we're doing is similar to that. Like I said, there's a lot of exceptions, 2 full years at least that I could go through and teach you just the stuff that I've seen in my structural detailing. And I know I haven't seen everything. So being able to visually understand what those lines represent, you know, these hidden lines inside there, these outside lines representing the toe of the flange, all represented by one single line. That's, like I said, one of the hardest things for students to grasp is if I tell you, just like I was when I was in those seats, if I tell you take this number off, you can blindly go through and spin that little chart and say, all right, let me take that number off. But do you know why? Because it's not always that easy as just take that number off. Some of those beams that I showed you on here, where we've been doing just the beam to column web or beam to column flange. I told you I noticed a mistake on my drawing the other day to where I had beams going into the column that were too wide to fit inside the column. That can't happen. There's 2 physical objects, a column and these beams. They cannot occupy that same space at one time. That's something different than what we're doing. That's not a block. What that's called is cutting. What we do is we take that top flange right here and we'll do a little notch on it and a little notch on the other side, so that when that column is there, that one is now cut down to fit inside the flanges. What numbers do we use to cut it back? Well, this dimension we have to calculate. How far in that direction? We have to calculate that little notch right there. We have that. It's called cutting the beam though. What we're talking about up here is called blocking. So we would have to cut a notch similar to that on both sides to get that member once again to go up in there so that those angles get flush to that column, and then the bolts pass through, they tighten it up, everything's in a good connection. Like I said, that's not only gives them the bolted connection, but just the friction that helps also of those members being tightened up that tight against each other. Alright, so everybody kind of understanding the beam to beam. So what you've got on this first sheet right here with all the asterisks in it, some of the things that we haven't talked about on this sheet, your angles. So over there on the left and right side on the drawings that you've been working on, you had something that said, and then you had these two parentheses areas. This next one was your center to center. This last one right here was your gauge. There is a number that goes right here after those AAs. We're not going to worry about it, but I am going to tell you about some of this naming that we do. When we start a project, it's going to be angle A1 with a lot. Like I said, this is something that really varies company to company. A lot of them, and what I do, if they say just go ahead and do it, I will have my angles AA and then a number, starting with 1. When I start with that first angle on that project, bam, there it is. So what we've been talking about, our angles have been, and this is something else that shows up on those, I think they're in Blackboard. Our angles predominantly that we've been talking about have been 3 inches by 3 inches by 3/8 by whatever the number was from that sheet, how long they are. So that's talking about that angle that's in there that has holes in it, based on the number of holes that we tell it. One leg of that angle is measured, has and will measure 3 inches. The other leg could vary. It's normally going to be 3 inches, 3 by 3. But if we get into one of those scenarios, so you had 3 center to centers that we predominantly talked about, 3.5, 5.5 when we're attaching to the flange of a column, 4 when we're attaching to the web. This one right here will not work on a 3 by 3 angle. It will not work on an angle that both legs are the same, because your gauges that you calculate are going to push those holes too far out for that 3-inch leg. So this is normally going to be a 3-inch or a 4-inch leg if we've got 5.5 center to center. So the way I do it personally, the way I was maybe taught early, this first character is just telling them that it's an angle. The second character for me is that a 3 by 3 or a 3 by 4? That way they can quickly look at it and tell what it is without having to look at the bill of materials. And then this last value, like I said, starts with 1 when I first start the project, and I count my way up. But here's what you have to think about on jobs. When we do those angles in there, so these angles coming in right here, we know are going to be, they're coming beam to beam. So we know that is going to be 4 center to center every time. So we can then calculate the gauge of that angle based on that center to center. So what that is a 3-inch by 3-inch angle. That's our legs. These two values are the legs of the angle. This value right here is the thickness. and this is the length. Like I said, the length y'all told me on that one exercise, you had to look up on your beam row connection chart, and up at the top it said 1 row, 2 rows, 3 rows, 4 rows, and then right below the number of rows in parentheses, it told you a length. And I had y'all show that on that first little project that y'all did. That was the length of that angle in that direction. So if we had 2 rows, that one would have been 6 inches long. So for that angle right there, it would have been 0.6 for the length. If we have a 5.5 center to center, that one then has a 4-inch leg. We always write the longer leg first. So if we had one of the other ones, it would be an angle 4 by 3 by 3/8 by 0.6. So what I was telling you about the piece marks, if that angle is 100% the same, we can reuse that name. If this one was AA7, this one over here on this side is going to be AA7. That's where the 2 comes from. There's that quantity. There's one on this side and one on the back side. That's where the 2 comes from. So this one and that one, definitely the same piece mark. Same gauge, same angle size, same length, everything is the same. So we could call each one of these AA1. Maybe on the other end of this beam, it's attaching to a column flange. So that beam comes over here. We've got our clip angles inside there. We've got our beam coming back off of there. Holes going through the column. We do our math, we look up on the chart, we find that that one has a 5.5 center to center. Those will have to be a different piece mark. There is something different about them. 5.5 center to center, we know those are going to have 4 by 3 legs, not 3 by 3. So these would then carry the neck, actually they would carry a B. And we start that and we carry that on through the whole project. We might be on sheet 15, and as a detailer, if that angle is shown over there, it should be called AA1. Because it's a lot quicker and a lot easier for them to set up their dies, set up their machines to make those angles. And if they know they need 50 of them, they can set it up, boom, pop, 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 run them right through there, cut, punch, do all that real quick. But if we say we have 25 of them, they're gonna set it up, they're gonna do 25 of them. And they get through flipping through, and here comes AA 25, 27. AA 27 is the same exact angle. But still, they've got that time that they have to set that machine back up again to get it to correctly punch it. They're not gonna go through there and say, all right, let's see if we can find all of these together that are the same. They're not gonna spend that extra time doing that. They're gonna go, all right, here's AA1. They're gonna start working on that, and they're gonna cut however many they need. They're gonna say, all right, AA2, let's do that one. They're gonna do however many of those they need. Then when they come to that other one, maybe it's the same. They're not gonna know, they're not gonna worry about it. They're just gonna set the machine up based on that drawing that they're holding, that you, the detailer, made, and they're gonna make those angles. As a company, it's gonna be cheaper if we carry those piece marks all the way through that project. So if that angle comes up 25 sheets later in the project, and it's the same size angle, 3 by 3 by 3/8, same gauge, same number of holes, we're expected to use that mark again for that reason, so that they can go through and cut all of them at one time, instead of having to spend that extra time of setting the machine or the equipment up to recut the same thing. A lot of places have nesting software. Nesting software is, it just says you put all this stuff in it and the software will arrange it for you. So if you tell it, I need 100 of these angles, 100 of these angles, 100 of these angles, they're all the same size, 3 by 3 by 3/8, they're just different lengths. The software will go through and say, well, if I take this 12-inch one and stick that with the 6-inch one, this 3.5 inches, it'll say, all right, let me get this many sticks so that we don't have as much excess at the end. So that's something that some of your electronic equipment will do. The nesting, most of the nesting is done with structural steel. I haven't seen a lot of nesting in the piping industries and other industries like that. But in the structural steel world, it will take all of these bill of materials. So each one of these pages, we hadn't even talked about that yet, but each one of these pages, we're gonna have a bill of materials over there that says, to make this beam, you need one W12 by 30 by this long. You need 2 angles, AA1, 3 by 3 by 3/8 by 0'6". You need 2 angles, AB1, 4 by 3 by 3/8 by 0'6". And all of that electronic stuff is going to go into this kind of like a hopper. And that software is going to go through and it's going to pull all those that are the same size, 3 by 3 by 3/8, 3 by 3 by 3/8. And it's going to put all of those into a certain area in the computer. And it's going to put all the 4 by 3s over here. And then what it's going to do is you have to, the company will tell them, we buy 20-foot sticks, 20-foot lengths of raw material. So the nesting software will go through and nest and say which pieces need to come out of each one of those 20 footers so that at the end of the job, you're gonna have the minimal amount of excess left over. That's what a nesting software does. Nesting software and plate material. They start out with a big old sheet of steel plate, whatever thickness. They have the machines and the equipment. When I was at CB&I think they ran 10-foot by 40-foot sheets is what they were running on theirs. And I think it would go up to 1-inch thick steel that it would cut through. Some of them go a lot bigger than that. But so what it does is, on this software, you take all these different plates that you do. So maybe we have some gusset plates that come out and do weird stuff like this. Has all these bolt patterns. We're not worried usually about the bolt patterns, but sometimes they cut those too. Maybe you've got just some regular plates that look like this. And you've got all these weird shaped plates that come through there. It'll take all of those and position them, nest them to where it can get the best usage out of that piece of plate. The smallest amount of drop out of that piece of plate. It'll go through and spin that stuff around. In structural steel, like I said, I haven't seen it in the other industries. I'm pretty sure they have it in piping. I just haven't seen that deep into where the piping drawings go next. I've always worked with smaller fabrication type companies where they actually looked at it and said, okay, maybe they're typing it in an Excel spreadsheet. You know, we need this many feet of this size pipe, this many valves, this many elbows, stuff like that. So this number that we haven't been talking about, that's just a name for that piece of material. Remember, all this stuff is done in lots of times in different shops, warehouses, usually by the same company. But the angles are probably going to be in another big metal workshop over there, 200 feet by 100 feet. With all this piece of equipment in there, all these lifts and stuff in there, you're going to have one that does plates. Angles will be in a totally different area. Your handrail, even though it's angled, will be in a totally different area. Your I-beams, your heavy stuff is usually the main part of the shop, the big shop. They come together as pre-cut pieces. So once it comes together for the person to put that square on the end and say, let me weld these angles on here, let me fit these angles so you can weld them on there. When it comes to that person, it's already been cut to length. Any notches like these blocks or cuts have already been done to it. It's ready for the welding process. That's when the angles and the plates and the I-beams all come together for the first time. And that person's gonna look at this drawing and say, okay, I need this beam, boom, there it is right there. I got it sitting on the rack. So I need 2 of these angles for the left end, AA1. And they're gonna go over to a pallet that has nothing but just a bunch of angles on that pallet, bunch of pre-cut, pre-holes punched and everything sitting on that pallet. And they're gonna look at the little tags, little stencils on them. And they're gonna say, here's an AA1, here's another AA1, all right. I need 2 AB1s. They're gonna go back over there. Maybe that's a different pallet, maybe it's a different stack. They're gonna find 2 of them that are stenciled or labeled AB1. Now they're ready to put that piece together and start welding on it. But they've gotta be ready to go when they get there. So each piece that we put on here has to have full measurements on it, just like if it was on its own drawing. This plate right here, this plate, this, all of that would be welded to some kind of a column or beam. Eventually. First, it's gotta be cut. It's gotta be ground. It's gotta have holes punched or drilled in it. So in structural steel, we detail and dimension everything. We give everything a name or a piece mark, it's called, so that we can do that bill of materials. On the handout that I just gave you, on the bottom side of it, it says 1 beam This one says 2B, and then it's got the asterisk. This is the quantity. Sometimes there's one of these beams with these angles welded on the end. Sometimes we might have 10 of them that need to be built. That's the quantity of that overall unit. Sometimes it's just an I-beam with angles on the end like what we've been doing. Sometimes it's an I-beam, it's got angles on the end, it may have plates welded onto it that, for handrail. Holes all up and down it for different members tying into it. So the quantity right here, here's another little weird thing about structural that I'm not making you worry about, but just something to put in here. That number right there, your quantity of those units, those assembled, welded, whatever units that are going to end up going out to the refinery, if it's a quantity of 1, we spell it out. Anything else, we write the number. I'm not sure if way back when somebody got confused about the number 1 versus the written 1, but that's just something that's for structural steel. If it's a quantity of 1 of the units, we spell it out. Then we tell them what it is. Is it a beam? Is it a column? Is it a handrail? Is it grating? So this in the middle is just telling them what it is. All we're doing right now is beams. When we do a column, it'll say 1 column, and then the number. And then this over here at the end, these 3 characters or 3 sets of characters, the first number where I have 2B, the 2 represents the sheet number. So when I'm detailing a job, sheet 1, sheet 2, sheet 3, sheet 4, sheet 5, that's where that character comes from. Because if they call from the field, if they call from the shop, or if they call from whoever I'm doing the work for, and say, we've got a question on this beam, which beam is it? It's a W12 by 30, there's like 40 pages of those beams, so let's just go through and we'll try to find it. No, they're gonna say, I need to look at sheet 5, or we need to talk about beam 5B1. Boom, sheet 5, I'm looking at it in a matter of seconds. So that first character right here is the sheet number it's detailed on. The second character right there, B, just tells us that it's a beam. When it's a column, it's gonna say 1 column, 2C1 is what it would be for a column. So that's just telling them what that finished product is gonna be out in the field. It can be 2HR1 if it's handrail, 2TP1 if it's toe plate, G1 if it's grating, D1 if it's bracing, it's usually called diagonal, so it's D1. So there's a lot of different options for that, but that's all it is. This right here and this right here are related. It's a beam, therefore it's gonna be a B. If it was a column, it would be a C right here. And then the last character right there, the asterisk, would be what number it would be on the sheet. So like I said, structural steel, normally, we're always 1 inch equals a foot unless we have to do something different. Normally they're drawn on a 24 by 36 sheet of paper. On that 24 by 36 sheet, this is the first one on the sheet, second one, third one, that's what that last character is. So if I have 6 members, beams, handrail, grating, whatever, if I have 6 of those items on that sheet, detailed on that sheet, if it's beams, it's gonna be, if it's sheet 2, 2B1, 2B2, 2B3, 2B4, each one of those members. So once again, they call me up. I've got a 24 by 36 size sheet of paper with 8 different details on it, beam details. We need to talk about this beam on sheet 8. I'm looking at it, which one? Now they can say 8B1, 8B5. We know exactly which one to look at. So numbers like this in some of the larger companies can get a little bit more extensive. It's not as simple as 2B1 because it's a beam on sheet 2 and it's the first one you drew on that sheet. When I was at CB&I, everything that we did there in the drafting part was electronically designed to mean something else to other departments. To us as the drafter, it's just a number that we put on our page. But to purchasing and all these other departments that work off of that bill of materials, off of that drawing, to order the material, say what size we need to put it into the nestings, all of those people is what that code comes from. So once you get out into industry and you're not at just some smaller fabrication company, maybe even a bigger fabrication company that keeps it simple, you'll see stuff like this. If you get into some of the bigger companies that do several multi-million-dollar projects a year, big fabrication facilities, when we were at CB&I, we were on Island Park over, I think it's 20-something acres, and we had something going on the whole part of that facility. There was actual active work going on in each area of that thing. So when you have something big like that, and then CB&I, once again, is nationwide, worldwide, those bigger companies have the higher dollar softwares that'll go through and do a lot of stuff. So it takes that drafter that still can do it, but it makes it easier on them lots of times. But then we have stuff that we have to deal with, like naming it, that isn't just simple, because it's no longer just something that goes from the drafter to the fabricator or the fitter and welder out in the shop. It's going through purchasing, it's going through all these other departments, scheduling, it's going through all these other departments. So it's a code more than it's just a name. And here, like I said, I'm not gonna throw any of those twists at you. I'm gonna let you know if something does come up that I haven't stressed to you over and over and over, I'll try to let you know. If not, y'all, those of y'all that know me, know that I'm gonna give you allowances on the other end when it comes time. So, I want y'all to understand this. And like I said, the biggest thing, the stares I was getting the other night told me that y'all aren't understanding what you're drawing. Because if I can show you that 2x4 going between those two 4x4s, and everybody looks at me like, oh yeah, I know that. You go outside and see that in my house right now, that exact thing. But then we start talking about I-beams. If I'd have told y'all to draw a couple of 4x4s with the board between it, no problem. I start talking about drawing that I-beam, and that little drawing that you've been looking at, and that little slider that you've been working with. It isn't just lines. There's standards, there's norms, and there's stuff like that all through the structural industry. But the detailer has to look at stuff and say, oh, that's different. It happens regularly in structural steel. It's not cookie cutter. It's not just, I'm gonna do the same thing today, tomorrow, the next day, the next day. It's thinking about each piece every time. So this first handout that I gave you just shows you the spaces that you need to have stuff done. So once again, hopefully I'm not going over your heads. You will be drawing the beam with possibly blocks on it. Everybody kind of understanding that. You're understanding the shape and why we're doing that, and where to get those numbers from based on those shapes. What I want you to do for your next assignment, you will see this second page. That's for you if you want to go through and fill in the blanks and sketch it up before you draw it. But what you will be doing is from this previous assignment, that was, I'm gonna have to look at it real quick and see. I was too busy flipping around those other pages trying to find that board. Did y'all open it up though? Is that border and title block good?
Mm-hmm.
Yeah, okay. So the one that y'all were working on before, where you had your first beam to beam details, it was called beam details 2. These in the middle, number 2 and number 5, are beam to beam on each end. Both of those measurements are under 15 foot, 14 or so foot, so it shouldn't be a problem fitting on that 11 by 17 border. That is your next assignment, to draw those up in CAD on that 11 by 17 board. Now, those of you that fell for my little trick of throwing that 8.5 by 11 at you a couple of times, I don't know if you know about this, but over here on the annotate tab, they have a button right here in your dimensions section. That button is the update button. What that allows you to do is to change the scale and yet make your dimensions show with your correct numbers. So once you set your scale on that sheet that I gave you to 1 inch equals a foot, and you lock your scale, if you've got your previously drawn beams and now your angles are the wrong, your text is either too big or too small, as far as the dimensions, you can use that update button, that update command, to tell AutoCAD I changed my scale, go through there and fix my arrowhead size and my text size and everything like that. As far as your written text, like your minus dimensions and stuff, yes, you're gonna need to go through there and change those. I'll put that chart in Blackboard for you. Drawing factors is the name of the sheet. He left. Yeah, he was bringing his had some food or something. So he's coming back. He's supposed to be coming back very shortly, so he should be walking in. I thought he would be back at 6:30 actually. Yeah, if not, if I see him come in, I'll tell him, I'll send him to you.
Oh, thank you.
So that's the easy way to change your dimensions. As far as changing your text height, the easy way to do that, once you look at that chart and see what your text height needs to be, just go around and click all of the text options that you have. So I've got some text on these. And then just go over there to your properties dialog box, change all that text height one time. Remember, use that chart that I put for you in Blackboard. Also, after you change that text height, you might want to zoom in to make sure you don't need to move them and recenter them and stuff like that. Because chances are, depending on your justification, that probably caused some problems when you went through there and changed all those text heights. Any questions on what you're working on? I'm gonna go ahead and raise that back up a little bit in case y'all need any pictures. That's it for today. We will be having another test coming up pretty soon.